Okay, so in this last part of the Chapter 7 notes, we're going to be talking about radicals, which is another word for a root, like a square root. So we kind of use those two words interchangeably, radical and root. So when we think about square roots or higher roots, we'll talk about in a minute, I like to think of a square root or any root as a question. So to me, what this is asking, square root of 16 means what number multiplied by itself equals 16. Okay, what number multiplied by itself equals 16? That's what it's asking. So in that case, then, if I think about what number that would be, it would be 4, right? So the square root of 16 equals 4, just 4, no more square root sign, because I've answered that question, right? If we think about that question kind of has that, that square root sign has that question with it, then I don't need that question anymore because now I just have 4. This, it might be a little hard to see, but this next one is a cube root. There's a 3 in the little crook of that root sign. So this type of question means what number multiplied by itself 3 times, because of that cube root, right, equals 8. So it doesn't mean what multiplied by 3 is 8. It means what multiplied by itself 3 times equals 8. So if we think about this one, just so we get an answer, 2 times 2 times 2 is going to equal 8. 2 times 2 is 4. 4 times 2 is 8. So again, then the cube root of 8 is going to be just the plain old number 2. Okay, so we could think about this with any root also. If I had a 5 in there instead of a 3, fifth root of something, it would mean what number multiplied by itself 5 times equals that. And sometimes when we take a square root, we get an integer, or any root, we get an integer like we see here. And sometimes we get a decimal. And we talked about this earlier in the semester when we talked about irrational numbers. And we said that anytime you have take a square root of a number that's not a perfect square, you get an irrational number. So if you have your calculator handy, you might want to try that. You might want to take, for example, let's take the square root of 16, we'll see we get 4. If you take the square root of 17, we're going to get a decimal, 4 point something. Okay. Well, if I jumped up and took the square root of 25, I would get 5. So everything in here from the square root of 17 all the way up to the square root of 24 would give you 4 point something, right? Because it's between 4 and 5. These are going to be irrational numbers. They're going to be decimals that go on forever and ever. Okay, so let's think about what are some perfect squares. What are those numbers? So a perfect square means its square root is an integer. Okay. What are some perfect squares? Well, if we think about how to get these, the square root of, if I think about getting a perfect square, I'm thinking what number am I multiplying by itself to get that number? So 1 times 1 is going to be 1. 2 times 2 is going to be 4. So 4 is a perfect square because it has an integer 2 that multiplies by itself to make it. Let's see, 3 times 3 is going to be 9. 4 times 4 is 16, 5 times 5 is 25. So these numbers that I'm writing are the perfect squares, and I'm finding them because I'm creating them by multiplying a number by itself. So 25, 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, 10 times 10 is 100. They go on forever, right? I could take 5,373,000 and multiply it by itself and get a number that's a perfect square. But 100 is kind of a nice place to just stop. Sometimes we run into ones that are bigger than that. But okay, how about perfect cubes? So in a perfect cube, its cube root is an integer. So again, I can come up with a list of those by thinking about, okay, if I take a number and multiply it by itself 3 times, what do I get? That answer would be a perfect cube. So 1 times 1 times 1 is 1, 2 times 2 is 4, times 2 is 8, 3 times 3 is 9, times 3 is 27, 4 times 4 is 16, times 4 is 64, 5 times 5 is 25, times 5 is 125, okay, etc. So each of these is some integer multiplied by itself 3 times. How about perfect fourths? Just to kind of keep going here, the fourth root in this case is an integer. So again, think about, okay, if I take a number and multiply by itself 4 times, it's always going to be 1, right? And then 2 times 2 is 4, times 2 is 8, times 2 is 16. So this one is 2 to the fourth. 3 times 3 is 9, times 3 is 27, times another 3 is 81. So this is 3 to the fourth. 64, so 4 times 4 is 16. 16 times 4 is 64. 64 times 4, I don't know off the top of my head, so let's see over here. 256. 5 times 5 was 25, times another 5 was 125, times another 5 is 625. See, they get big very fast, right? Okay, so it's going to be important, especially perfect squares and perfect cubes, to recognize them and also to be able to figure out, if you say, I think 125 is a perfect cube, but I'm not sure, then make sure you know how to find the cube root on your calculator. And if you don't, go ahead and ask me, okay? I'm not going to go through it too much right now because everyone's calculators are slightly different, but in general, to find the cube root, to find the square root, there's probably just a square root button. And you probably, it depends on your calculator, either put that in first if it's the kind of calculator where it shows you what you're doing, and then you would put your number in, or if it's a calculator where it doesn't display everything you're writing, you might have to write the number first and then the square root. So kind of play around with that with numbers you know. Cube root, there may be a cube root button or function, or it might be kind of like this with an X. In that case, if you wanted to find the cube root of 8, you'd probably have to do cube, like put in 3, then put in this button, and then put 8. Okay, but play around with it a little bit with numbers that you know the answer to, just to see, and if you have trouble, then certainly let me know. Also, if you Google your model of calculator, there are most likely some, instructions or videos or whatever online too. Okay, so we're going through a couple things here that kind of seem unrelated, but then we'll bring them all together with our examples. So the next two things we want to talk about are the product property of radicals and the quotient property. So we know those words, right? The product means we multiply, the quotient means we divide. So this is really simple. All it's saying is that if I have two roots, two radicals, and they're being multiplied, I can multiply those things under one radical. Now this works as long as it's the same kind. If this is a square root and this is a square root, it's fine. If one is a square root and one is a cube root, then I can't combine them, okay? Because your combined one has to have the same kind of root as both of your individuals. Also, I can go the other way. So if I have something here, I can split it up. So let me show you an example to make more sense. Let's say I have the square root of 5 and the square root of 8, okay? I can go ahead and write that as the square root of 40. Or if I have the square root of, let's say 60, okay, I can split that up into any two factors that multiply to be 60. And we'll use this again. You'll see why we use this in a few minutes. Quotient property, same idea, but for division. So if I have two separate radicals being divided, I can put them under one radical sign. I can also go the other way. I can start out like this and break it up. So, for example, if I have radical 75 over radical 3, I can put that together. And you might see why I want to do this in this case, right? 75 divided by 3 is going to be 25, which in this case is going to be a perfect square. Whereas 75 and 3, we can get there, but it's not as nice and neat. Okay, so it's the same idea. You can pull it apart, you can put them together. Okay, now we have talked about perfect squares and cubes and everything dealing with numbers, but let's look at variables now. Okay. And so this says, and this is going to sound like a mess when I first read it. Okay, so just hang with me here. A variable with an exponent is a perfect root if the exponent is divisible by the index. Okay, so what in the world does that mean? So let's say I'm trying to take the root of x to the 8th power. So here I have a variable with an exponent, okay? So it is a perfect root, a perfect square, a perfect third, whatever it is, if the exponent is divisible by the index. So actually, let me color code this for you. So if the exponent is, which is right here, here's my exponent, if that is divisible by the index. Well, what in the world is the index? The index is what tells us if it's a square root, a cube root, a fourth root. So my index is whatever number is right here. Okay, now in a square root, there's actually nothing written there, but it's implied that it's 2 because squaring something is 2 times, or multiplied by itself twice, right? So if my exponent is divisible by the index, can I do 8 divided by 2? Yeah, right? It's going to be 4. It's divisible and it's 4. That means that this is a perfect root, and I can answer that question just like I would with numbers, and the answer to this question is going to be x to the 4th. So what's the square root of x to the 8th? Or in other words, what expression multiplied by itself equals x to the 8th? It's x to the 4th. Does this make sense? Let's check it. X to the 4th multiplied by itself. Well, think back to our product property. We add those. Absolutely, that's what we get. Okay, let's do another example. So let's say I have the 5th root of x to the, 35th. Okay. Now, what sometimes people get confused about is that we're not looking at whether 35 is a perfect fifth or a perfect square or anything. What I'm looking for is if that exponent of 35 is divisible by my index of 5. Can I take 35 and divide it by 5? I can. So because I can divide it, that means I can get an answer for this. And whatever the answer is when I divide is going to be my new exponent. And again, if you think about this, if I had one of two ways, either x to the 7th multiplied by itself 5 times, or if I had x to the 7th raised to the 5th power, either way, those give me x to the 35th. Okay, so we're going to put all this together now. It seems like a lot of nonsense. We're going to put it all together. We have talked about radicals. We've talked about perfect squares, perfect cubes, pulling them apart, putting them back together, and variables. Okay, before we go on, let me just remind you here that it must be, for both of these, the same index. Okay, so, or in other words, they have to both be square roots, both be cube roots, whatever. So, okay, so we want to simplify these now. And to simplify it means to take as much as possible out of the square roots, or the whatever kind of radical we have. And I will tell you that for these first few, this first bunch actually, we'll be able to basically always take them right out of, what are we trying to do? Take them right out of the square root altogether. Okay, we didn't mess up something here. All right, there we go. Okay, so simplify these radicals. What I always like to do first is I like to rewrite it so that each portion has its own square root sign. Then I'm just thinking about numbers, just thinking about x's, just thinking about y's. And we know we can do this from that product rule, right? So you don't have to do this. I always do, because I just think it's a lot easier to work with. So now I'm looking at each part separately. So I have square root of 16. Well, I know that that is a perfect square. Square root of 16 is just 4. Now I'm looking at the square root of x to the 4th. So again, I want to know, is my exponent divisible by my index? Remember, I'm just going to write these in here, even though they're not usually in here. My index is 2 for a square root. So can I take 4 divided by 2? I can. 4 divided by 2 is 2. So there's x squared. Can I take 6 and divide it by 2? I can. It's 3. So my answer then is 4x squared y to the 3rd. I cannot combine the x and the y. We know that from before. If I want to check this, think about how I could do this. So I'm going to check this now. So if I think about 4x squared y to the 3rd, and I want to know if this is squared or multiplied by itself, what will it equal? Well, 4 times 4 is 16. X squared times x squared is x to the 4th. Y to the 3rd times y to the 3rd is y to the 6th. Yes, I got what I started out with. Another way you could have checked it is to say I'm going to take this whole expression to the 2nd power. Remember there's a 1 there. You still get the same thing using that power rule. Okay, let's look at this one. So now I have a quotient here. I have a choice. I can split it up into radical 75 over radical 75x to the 7th over radical 3x. That's fine. But if you look at those numbers, it's really not going to help me. What's actually going to help me, this is similar to my example in some ways, is to leave it like this and do the division inside. So let's do that first. So 75 divided by 3 is going to be 25. X to the 7th over x to the 1st, 7 minus 1 is 6. So I have this. Okay, now, how did that help me? Well, now if I look at this, I actually have 2 perfect squares. Square root of 25 is going to be 5. The square root of x to the 6th is going to be x to the 3rd. Think about how I got that. 6 divided by 2, the index, is going to be 3. Okay, in number 3, there's actually a typo in here that I'd like you to change will match the completed notes. So this right here, oh, that's not very good, should be, instead of being a 4, we're going to make it into a 6. Okay, so we're going to have cube root of 27x to the 6th. All right, so again, I'm going to choose to split this up. So cube root of 27, cube root of x to the 6th. Cube root of 27 is going to be 3. Cube root of x to the 6th, 6 divided by 3, I can do that. It becomes 2, so I get x squared. Okay, let's look at number 4. So number 4, I have 2 different expressions. They're both square roots, so I know I can combine them or I can leave them separate. If I look at what I have in these, though, not one of these parts in either of these square roots is currently a perfect square. So if I leave it separate, I really can't do anything. But since I can divide, or since I can multiply them together, let's try that and see if that does anything for us. So I'm going to multiply this out to one big square root. So 20 times 5 is going to be 100. X to the 5th times x to the 7th is x to the 12th. Y to the 3rd times y to the 5th is y to the 8th. Okay, so let's just go back and make sure you see how I did that. I just multiplied my numbers, then my x's, I used the product rule, and my y's, I used the product rule. And they're both inside, they were both inside square roots, so my answer also has a square root. So if I look at the numbers I have now, the really good thing is that now I have 3 perfect squares. I have radical 100, I have radical x to the 12th, and I have radical y to the 8th. Square root of 100 is 10, square root of x to the 12th is x to the 6th, square root of y to the 8th is y to the 4th. And there's my answer. Now, sometimes people get confused and keep a radical too long in the process. Maybe they write a radical in this circled part somewhere. But remember that once you've answered that question of what number or what expression multiplied by itself equals whatever you're starting with, then there's no more square root. Okay, so once you've taken that square root, the radical sign goes away. Okay, so there's another page here. You can see there are 6 more examples. We're going to get to those in a minute. Let's do this part about the root of a negative number and simplifying these that are not perfect squares, and then we'll go back and I'll encourage you to pause the video, try those other ones on your own, and then I'll have the answers on there. Okay, so let's talk about if we can take the root of a negative number. So we talked about this a little bit, I think, in chapter 1. But if I try to take the root of a negative number, okay, I'm going to say there's no solution in the real numbers. I cannot take the square root of a negative number. Now, the reason I say no solution in the real numbers, if you remember when we talked about number sets, there's another whole set of numbers called imaginary numbers, and that's exactly what that deals with. You'll talk about that in Math 120. Okay, so why is it that there's no solution? Well, think about this. If I want to look for what number multiplied by itself equals negative 9. So if I take 3 times 3 is 9, so that's not going to work. But if I take negative 3 and multiply it by itself, well, a negative times a negative is still a positive, so that's not going to work. Okay, what if I take 3 times negative 3? Okay, that's negative 9. But remember, for a square root, it has to be a number times itself. This is not a number times itself. Okay? So this doesn't work either. So there's no solution. The only way to make that negative is to have different signs, but in that case, then I'm not multiplying a number by itself. I'm multiplying a number by its opposite. But let's look at cube root of a negative. I can do that, okay? Because if I want it to be, I know that cube root of 8 is 2, right? Well, the cube root of negative 8 is going to be negative 2, and that's going to be okay. Let's see why. So negative 2 times negative 2 would be positive 4, and then positive 4 times negative 2 would be negative 8. So that does work. That's like an awful check mark there. So that does work, okay? So why is that? Well, think about what happened here. In this case, we had, up here we had 2. In order to have a number multiplied by itself, I had to have either 0 negatives or 2 negatives, and 2 negatives combined to make a positive. Here, I had 3 negatives, and whenever I have an odd number of anything, no matter what it is, so odd numbers, when we make pairs, there is always one left over, right? If I have an odd number of people and I make groups of 2, there's always going to be one person left over. So that is an important idea here. I had my 2, I paired these 2 up, right? These 2 paired up to be a positive 4. Then there's this extra that's going to turn it negative. So that's always going to happen when we have an odd amount of negatives, an odd number of negatives. What caused us to have 3 here instead of 2? It was the index. So the rule overall is then we can take the root of a negative number when the index is odd. So for example, cube roots, fifth roots, etc. Okay, we cannot take the root of a negative number when the index is even. So if it's a square root or a fourth root, then we cannot take it, because if it's an even index, that means it's an even number of numbers I'm multiplying, and even numbers of negatives would always match up to be a positive. Okay, now the last little part of this is when we're looking at radicals that are not perfect roots. So in those examples we did before, they always came out to something like, the square root of x to the 10th, or the square root of 25, or something that is a perfect root. Well, here we're going to look at some that are not perfect roots. So what we want to do in that case is we still want to simplify whatever part we can. So we look at the factors, the things that make up that number or that expression, and we want to factor it and pull out the factor that is the biggest perfect square. So this is where you really need to also kind of recognize your perfect squares. So if I'm thinking about 50 here in number 9, let's think about factors of 50. And remember how we wrote these out, really orderly, right? So 1 times 50 go up to 2, 2 times 25, 3 and 4 do not go into 50 if you check in with your calculator, 5 times 10, and then 6, 7, 8, and 9 don't go in either. So if I look at this, I have a couple of perfect squares here. I have 1, 1's always a perfect square. 1 doesn't really do anything, because if I factored it, it would be 1 times 50. That really doesn't help me, so we're never going to use 1. I also have 25. And I see that 25 times 2 multiplies to be 50. So I'm going to use that product rule for my radicals to separate this out. Now, I always write my perfect square first. So I'm going to use this pair right here, 2 times 25. I'm going to write my perfect square first. So square root of 25 times the square root of 2. Product rule says it still has to be in the radicals, right? Okay, square root of 25 is going to be 5. I can't simplify my radical 2, so I just leave it. When I can't pull anything else out, because radical 2 only has one pair of factors, 1 and 2. Doesn't do anything for me. Now, if you want to check it, you can plug radical 50 into your calculator. You'll get a big long decimal. It'll be irrational, right, because it's not a perfect square. Then you can do 5 times radical 2 and make sure you get the same big decimal, because we didn't change anything here about this number. We just changed the way it was represented. Radical 25 is the same as 5. Okay, let's look at number 10. So now I have 32, the square root of 32x to the third. So again, I'm going to split this up. So I'm just looking at one part at a time. Okay, so 32. Now the more you know your multiplication, the easier, but you can always just recreate the list of factors like we have been doing. So 1 times 32, 2 times 16, 3 does not go into 32 evenly, 4 times 8. If I check 5, 6, or 7, they do not. So I'm looking here and I see a few different perfect squares. 1, as always, 4, and 16. So I want to go with the biggest perfect square. So that's going to be 16. And I'm going to use then 16 times 2. So I'm going to rewrite radical 32 as the product of these two radicals. I'm going to write 16 first because I put my perfect square first. And then we can keep going with this part if you want, right before we move on to the x's. Square root of 16 is 4. So it's 4 radical 2. Okay, let's look at x cubed now. So x cubed in this case is also not a perfect square because 3 is not divisible by 2. So basically what we want to do in this case is we want to split this up, and we want one of these to be the biggest number of x's, okay, the biggest chunk of that x to the third, that is divisible by 2. So if I have 3 of them, I want to know, okay, let's take the biggest group of these. The exponent would be divisible by 2. So in this case, it would be 2, right? I can take 2 of these. X squared is divisible by 2. That would leave x to the first here, because these 2 still have to multiply back to get us x cubed. So I take off one of them. I pull one of them apart so that these 2 in parentheses, this is a perfect square now. Square root of x squared, well, 2 divided by 2 is 1, so this is just x, or x to the first, and then I have radical x also. Okay, now to combine these two, I can always combine any outside numbers, outside the radical, and combine inside the radical. So I am going to take, switch colors here, 4 times x, that's going to go outside the radical. I'm just going to put a little spot for it right here while I have that highlighter. And then I'm going to take what's under the radical, radical 2, and radical x, and that's going to go here in this part of the answer. So my answer altogether will be 4x times the square root of 2x, okay, or without all my crazy color coding, it will look like this. Now, you might think, well, that doesn't really feel like it's any simpler to me, but you just kind of have to trust me that this is, how we simplify it, right? We've taken out whatever we can that is in the way of that being a perfect root. So let's do the last 2 here. Are there more at the bottom? Nope, just a blank page. Okay, so this is a cube root. I know these are a little hard to read here. I have to make them a PDF when I upload them, especially because if someone doesn't have Microsoft Word, these don't open up correctly. So, okay, so we have the cube root of 250, and we have the cube root of x to the 5th. Now, we don't probably know the cube roots of 250 as well, or cube roots of anything, perfect cubes. We can write out all the factors again. Also, if we look back at our list, let's see, way back here, our list of perfect cubes, we may be able to find one in there. We can kind of check those, right? 250 divided by 8, 250 divided by 27, see what comes out evenly. And you actually kind of want to start from the higher ones. So if we do that, go back to where we were, we find that 125 times 2 would equal 250, and 125 is a perfect cube. So we can have the perfect cube of 125 and the perfect cube, sorry, not the perfect cube, the cube root of 125 and the cube root of 2. Cube root of 125 is 5, so this part ends up being 5 times the cube root of 2. Okay, now this part, again, 5 cannot divide evenly into 3, or not divide evenly by 3. So I need to figure out the biggest chunk of this x to the 5th that I can take out that would have an exponent divisible by 3. So if you think about it, if I just had, I could have x to the 1st, x to the 2nd, if I had both of those, x to the 3rd, x to the 4th, or x to the 5th. Well, x to the 3rd is the biggest that I can have that's divisible by 3. So if that happens, I'm going to have x to the 3rd times x squared, right, to make 5. So I have cube root of x to the 3rd, cube root of x squared. 3 divided by 3 is 1, so that ends up being just an x. That was my perfect cube. And then cube root of x squared. Similar to what we had before, I'm going to gather the outside numbers. So here's an outside number or variable. And then the inside numbers. So I'm going to have 5x times cube root of 2x squared. Okay, you go ahead and try the last one. So I'm going to say my hint is, again, to split it up into 4 parts. So the square root of the square root of a to the 7th, the square root of b to the 3rd, the square root of c to the 8th. If it's a perfect square, just go ahead and simplify it. If it's not a perfect square, pull out the biggest perfect square you can find. So pause the video, and then when you come back, you can check your answer. Okay, so let's take this step by step. If I look at the square root of 18, this one probably jumps out at you, knowing that 9 is a factor. It's the biggest factor of 18 that is also a perfect square. This would give me 3 radical 2. Okay, let's look at a to the 7th. 7 is not divisible by 2, but if I just take 1 away, which is what's going to happen with square roots, right? I get a to the 6th times a to the 1st. A to the 6th, square root of that is going to be a to the 3rd, and then I just have an a in my radical. B to the 3rd. Again, 3 is not divisible by 2, but 2 is. Square root of b squared is b, and I have a radical b. And finally, square root of c to the 8th. Well, that is a perfect square. 8 is divided by 2, so this can be c to the 4th, which just comes down. Now again, outside numbers outside the radical, numbers or variables, can get combined together when we're multiplying like this. So 3, a to the 3rd, b, c to the 4th. And then my stuff in the radicals is also going to get combined. So square root of 2ab. Okay, so 3, a to the 3rd, b, c to the 4th, the square root of 2ab. I've pulled out whatever I can that is a perfect square. All right, so now I would like to go back to these other examples. There are, let's see, we did those 4, so there are 6, I think, on this page that we didn't do. So go ahead and pause the video, try these. So if you're looking at the notes, this is on page 9. Okay, go ahead and try those and then pop back and you can check the answers on here. I have the answers written on here. They're also on the completed notes. And then if you have questions on any of them, you can always ask me during class next week or during office hours. All right? So go ahead and pause the video and then try these and come back to check your answers. Okay, so here are the answers to these. I'm not going to go over every single detail of these. Again, you can pause the video, check your answers with it, and then I'll scroll down. And if you do have questions, let me know. The main things I want to remind you of are that you're, in each case, if you're dealing with variables, you're dividing the exponent by the index. All of these on this page were perfect roots, right? We didn't have to do that like we did on the last time or take out just part of the factor. So there are the first 2. Here are the second 2. Now in number 4, I could have chosen to try to do each part separately or to put it together, but when I look at each part separately, what I originally have, none of those parts are perfect fourths, so I can't do anything with them, right? None of those variables are divisible by 4, and 25 is not a perfect fourth. So, but by multiplying them, then I created x to the 12th, y to the 24th, and 625 is the number. Those are all perfect fourths. And you can pause if you need a little more time with those answers, and then going down, here are the last 2. So in number 6, again, I had to multiply those together. So I multiplied the outer numbers together and the inner numbers together. So this is all, oops. Oh, that's not what I meant to do. So this is all under a radical still. And then I split that up. Took the square root of both parts, and then 10 and 12 are just both numbers, integers, outside a square root. There's no more square roots at all, so I multiplied those back together. All right, so if you have any questions on any of this, please let me know. Thanks, guys.